Classical Physics Tutoring Chapter 4, Section 1, the Basic Law of Thermodynamics. Okay, the thermodynamics, we're going to introduce something new out of Newton's mechanics. The Newton's mechanics, we defined the kinetic energy and the potential energy. Now, we never talk about heat energy, but we talk about this a little bit when there is a friction. The friction take out some of the kinetic energy and it's converted to heat energy. But what is heat energy? It's a molecule vibration and electron vibration, both. Okay, so this is micro levels behavior is out of classical physics, so we didn't talk about that. But the thermodynamics is an attempt to use Newton's mechanics apply to the micro level particle behavior. So for example, the gas, we consider the gas is a bunch of flying molecules in the random direction in the balloon, and we try to see if we can come up with the pressures and temperature and other parameters we want to know using Newton mechanics. And this is called statistical thermodynamics. And without this approach, thermodynamics is basically very dry. It's just a relationship between pressure, temperature, and the volume, and the heat energy, kinetic energy, and others. So it's just a relationship. You define the equation and you don't talk about mechanism underlining of those relationship. That's the classical thermodynamics. But we start going this direction first. Let's see how well we can use Newton's mechanics to explain some of thermodynamics phenomenon. And now, in order to do that, we have to define certain things. What is heat energy, right? So in the Newton's, before we define F equals ma, A and V, these are preconceived concept, and Newton didn't talk about it because all the Galileos and other scientists already kind of defined. You think about it, what is V? V is something the human can see. The human can see something moving faster or slower. It has a perception. So human sense kind of tell whether the speed is fast or slow, and we make it the scientific x meter per second. Okay, and using that speed we define the basic formula. We have to do the same approach in thermodynamics. The first of all, something related to speed is in thermodynamics called temperature. And what is temperature? Human cannot see the temperature, but human can touch and feel it's hot or cold, right? And how do you express this numerically? Okay, so it's a preconceived concept of temperature existing. Okay, now, so what is the temperature? We need the first law to define the temperature scientifically. The first zeroth law is zeroth law. You know why is this zeros? The scientists didn't think about necessity of this in the beginning and start with the first law, second law, but they go back, oh yeah, I think we need one. Let's put the zeroth law, okay? and that's why it's got the name of zeroth law and law of thermal equilibrium. And basically what it's saying is when you have A and B are thermally equilibrium and A and C are also thermal equilibrium, then the B and C are thermal equilibrium. That means there is a universal quantity that you determine for A, then it's good for B, good for C, you can compare. So what is it? Thermal equilibrium. Without defining the word thermally equilibrium, it's defined the zeroth law of the zeroth law of the thermodynamics. So it's kind of chicken and egg, which one you define first. But I think the correct way to say is when you touch your hands with your hands something you feel hot or cold, okay, and that is a good measurement. Now in order to make a science out of it, we have to define so-called temperature. It's a state, thermally equilibrium state. Okay, this is a state. It's like Newton's mechanics. You define the speed, and the mass is going at the speed. So think about it. What does it mean? Well, when you see it, it's kind of moving at the uniform speed, right? The same thing here. Thermal equilibrium state. And how do you define thermal equilibrium state? Okay, now that's where the thermometer was invented. The thermometer, they use mercury or alcohol, depend on the thermometer. This expand by temperature. If you give a heat, it's expand, and within a narrow glass tube, when it's expand, the height goes up, right? Okay, so this is the state of A, and you measure B and you measure C. If it's the same state with this A thermometer, then when you connect them together, B and C are equilibrium. Okay, so we have to establish thermal equilibrium, and tool is thermometer. We use a thermometer, and the idea is there is a heat energy. If it's not equilibrium, it's moving. Some kind of heat energy is moving into it and become equilibrium. Okay, so if not equilibrium, you see the difference, that the delta T, and the delta T, this is energy. How much energy you have to move to change the state by delta T. Okay, so there is a constant here, and the constant we separate into mass and heat capacity. What heat capacity? Heat capacity is this constant. In order to change the temperature by delta T, by energy delta H, there is a constant. The constant is made of mass and heat capacity. What is the heat capacity? This is the coefficient for each material, and for water it's 1. Many other things is less than 1. Okay, water is considered one of the highest heat capacitance. Okay, so this is the basic idea. Energy flow when they make a contact. Even they don't contact, energy flow by radiation, right? And this, say moon is radiating light, and you receive this, you heat up, and there's no way you can tell this equilibrium until you put the thermometer here and the thermometer here and compare, right? Okay, so the method of moving energy is not in the question here. We moved delta H and temperature delta T change. So this thermometer has a certain heat capacitance. Heat capacity is very little. The reason is you don't want to take too much energy, then it's changed the state of B when you measure. This is very tiny. Like you dip this into the bathtub, and heat energy you take from bathtub is very minimum. This state is unchanged. Only this state changed. Okay? So as you know the scale, we have two different scale. K is Kelvin, and the K is 0 means absolute 0. You cannot be lower than this. And as I said, the temperature is a molecule and electrons movement in the substance, and K is 0 means the movement stop. It's considered that all the atoms stop the vibration, the electrons set to the position, and it doesn't wander off to the other atoms, and that's a K is 0. C is made by the scale for water to freeze, which is 0, and water to boil, which is 100. But this is at the sea level, because water boiling temperature depends on the pressure, and if you go to the high mountains, it's boil easily. You know that, right? So that's the significance of the zeroth law. And now this is the first law, and this was more important in the beginning when scientists started thinking about this thermodynamics theory. Okay, and within isolated system, what is isolated system? Thermodynamics, we often use isolated system. That means there's no energy exchange from outside the world within this boundary. This is isolated system. Okay? And work is done. This isolated system has energy, heat energy, kinetic energy, and the potential energy. And this change around by conversion, but U is always same. Okay? So in this isolated area, energy stay same. Energy is conserved. Okay? So if somebody say, okay, I designed a machine that just keep moving forever. So this machine keep moving. Okay? And we take this as an isolated system. Okay? So the so-called perpetual machine, people often say, oh, I designed a perpetual machine. What's happened? Well, within this isolated area, total energy is same, U. Okay? Now, it may be spinning. It's a kinetic energy, but has a friction, so it generates heat energy. And maybe the movement is done by potential energy. This sum is always total U same. Okay, so if you claim it's perpetually spinning, whatever the perpetual machine, then friction keep increasing. That means potential energy and kinetic energy is going to be reduced. And you cannot do it forever, because eventually everything converted into the heat energy and the machine stop. Okay? So you can predict the machine is going to stop eventually according to the first law of thermodynamics. And if you claim you designed the perpetual machine, you are challenging the physics law, and you better be prepared, because millions of scientists and engineers go against you, right? So better not to propose a perpetual machine, because you will be defeated. Okay. Now, second law, irreversible process. This is very interesting subject in thermodynamics. Okay. The irreversible, what irreversible? Suppose balloon, you give a heat, right? In the heat source you see here, and this is isolated area. You give a heat, balloon expand. That means kinetic energy increased, right? And you return the heat, and it's shrink. So if you can repeat this process, right, without losing any heat energy, it's a potential energy increase kinetic energy, and the kinetic energy is returned back to the potential energy, and heat loss is zero. Then you keep repeating this, okay? And it's kind of perpetual machine, right? If you can do that, okay? So this is reversible. Okay. Usually perpetual machine said you can get the energy out of it, and no, you can't. Once you get energy out of it, this energy total energy get less and less, eventually diminish all the energy. Reversible is you don't get energy out, but you can convert kinetic energy to potential energy, and potential energy to kinetic energy. It should just go back and forth without generating any heat energy. Okay, why heat energy is important here? Once you have a heat energy, then it's not reversible anymore. Every time you repeat, you lose some energy to the heat. That's reversibility. Okay, and how do you measure this system's ability to keep the loss of heat energy? There is a quantity called entropy, and irreversibility means it's increased entropy. If this process increases entropy, that means it's not reversible. Some energy is changed to heat energy within this isolated system. Okay. Why this was important in the Industrial Revolution? That time thermodynamics became very important. The engineer was thinking about efficiency of steam engine. So steam engine, basically the heat energy changed to kinetic energy, right? The steam produce the shaft cranking machine. That's what it is. So in this process, some heat are lost, right? And if no heat is lost, efficiency is 100%. And using this kinetic machine, you can generate heat again. This is reversible, 100% efficiency. And that's what the engineer was looking for. But there is always energy loss from heat to environment. And they measure this as entropy. How much energy loss you have. And because of that, the efficiency decrease. Okay? That's the history of entropy. Entropy came from there. But it was the beginning of discovering much more important scientific concept of entropy later. So we talk about that in the next video. So irreversibility means increasing entropy, and you heard about it. In this world, entropy keep increasing. Why you say that? Because there's no process that 100% reversible, 100% efficient. There is always some energy loss, heat energy loss. Okay? And what does it mean from the micro particle viewpoint? So there is a very significant meaning on that. So the second law is about irreversibility of the process, and the third law was kind of added on. In the beginning, there was only first and the second, and in order to make it science, scientists said, oops, I think we need to add zeros, right? And later they said, you know what? I think we should add the third law to make it complete. So in the beginning, first and second was the most important. Then scientists added the zeros and third. Okay, so what is the third law? Entropy is zero at absolute zero temperature. And this one needs a little bit more explanation. But the absolute zero gives the zero entropy, and that's kind of related to this subject. And we go through in the next video, but this was just added to make entropy definition more precise. So the third one's added for entropy, and zeroth one is added to make the definition of temperature more precise. And having a four of them make it look like a nice science. Okay? And this claim, first and second, is nothing to do with Newton's mechanics. This is new law. Just like Huygens principle, right? Huygens principle is below the Newton. The Huygens exists first, then you apply Newton, then you know wave propagate. Okay, so it's not all about Newtons in the classical physics. There are a lot of additional law and principles added on to patch up the whole things. Okay, and later we add the electromagnetic. This is nothing to do with Newton, and special theory of relativity. And this guy defied the Newton's assumption. Okay, so that's the range of classical physics we're going to cover in this series of videos. I hope you enjoyed this video, and if you like, please subscribe.